with a tool named ChangeMod to assign permissions, or optionally, the English alphabetical representations RWX may be used. Either or may be used, and they're understood by the appropriate tools. So you're largely dealing with read, write, execute with respect to permissions that are associated with the owner, the group owner, or everyone else. So let's just note that the tool that's used to change these permissions is called ChangeMod or change mode. It's really to change the octal mode on the particular object or objects in question. So use ChangeMod to influence permissions on files or file objects, which of course includes directories, etc. ChangeMod changes the octal mode. So it changes the octal mode. Octal meaning 8 with permissions maxing out at 8, indexed at 0. Now by default, let's just note, see, default permissions are inherited from the umask variable, which is defined when a user logs in. So in a shell, for example, let's echo umask. Now when it's not set, it defaults to 2 defaults for files and or 1 per file or directory, which amounts to the creation of directories and files with specific permissions, 644, 755. So there are defaults that are assumed when you log into a shell environment if the variable is unset. There's also a specification in login.defs. Let's take a look at etc login.defs to see if we can extract the default umask that is set on a per user basis, and it's defined here as 077, and it tells us also that the permission mask will be initialized if it's not specified to 022, which means directories get created with 755 and files with 644. So the umask governs the default permissions, but of course, as an owner of an object, you can always change the default permissions to something that's more suitable using ChangeMod or using the GUI environment. But the umask, when set, will govern the permissions that are associated. So if we were to set the umask to something else in a given shell and then begin creating files and or directories, then the permissions would be influenced based on the definition of that umask variable. So we've got read, write, execute for a total of 7 per any group, owner, group, or everyone else. How do we influence these permissions? Let's take a look at what's happening in our home directory to see what may be of interest. Perhaps we'll look at the items 1,000,000 star and notice that they all seem to wear the same permissions. 664, read write, that's 4 plus 2, read write, 4 plus 2, that's for the owner and for the group, and read for everyone else, 4. So 664 appears to be the default permissions assigned to these objects, which means the owner Linux CBT has read-write access. Any member of the group Linux CBT, which defaults to the user Linux CBT on the Red Hat system, has the same permission, and everyone else may read the content but not make changes, and of course that can be tested. So to test that and then change the permissions, let's try to read 1,000,000.txt as a different user. So in a separate shell, we'll SSH as Linux CBT4. Let's just be sure that the user can actually log into the system with a valid shell, and indeed 4 can. So let's SSH as Linux CBT4 at localhost. This will give us a shell environment as this user, and once in, we're now in our home directory. If we LSL one level up, we see that Linux CBT's directory may not be entered by anyone else other than the owner. That means if we try to evaluate the contents of that user's directory, we're not able to. However, what if we copied the content to some other directory and made the file available with the same original permissions? So let's change into Linux CBT and let's copy 1,000,000.txt temporarily to /temp, a directory that everyone has access to. /temp now contains a copy of 1,000,000.txt, but the permissions are set to root because temp has the sticky bit set. So let's copy it to the root directory. Let's see what the permissions are on root's version of 1,000,000. Same thing, so we'll remove that version of it. It's writing it as root. So we'd have to chown it. We're not ready to use chown just yet, or change mod it and chown it. And we're not ready to use that just yet. So 1,000,000.txt now exists in temp, and it's read-writable by root, readable by the group root, and readable by everyone else. So as either user, we can, since root now owns the file, attempt to interact with the file. So let's nano temp 1,000,000.txt as a user like CBT4. So this contains the contents of the file. Let's try to add a new record, such as 0, and save the changes using Ctrl+X. Permission denied. We're not able to make changes to the file. We can read the file, but we can't change it. So let's exit, and then try the same as the user Linux CBT, who originally owned the file, but no longer owns the file. So 1,000,000.txt, it's going to load. Let's try to add a new entry, and then try to save the changes. Permissions are checked whenever disk I/O is performed. So when Nano loads the content into memory, you can make all the changes you want. But it's not until you attempt to write the changes to the disk that it will matter. So we'll not attempt to save the changes. So now the permissions are written on the file in such a way that neither user can make a change to the file. So that leads us into the tools that allow us to change these permissions, such as change mod. So let's move on. We're going to talk a little bit about change mod. The file sitting in temp is owned by root. So if we change mod, this time making it 666, meaning read write for everyone, temp 1,000,000.txt, all of a sudden either user Linux CBT or Linux CBT4 or any other user will have access to write to the file. But only the owner of the content can change the file in this way. And since root owns the content, root is able to change the file in that way. Let's reconfirm, and let's take a look. That's going to be temp 1,000,000.txt. So it's still owned by root, but now everyone, because of bits 8, 9, and 10, or 7, 8, and 9, depending on how you index the bits, is read-writable. So back in as Linux CBT4 for a moment, let's add a new record 0. Let's save the changes, and it's saved. That means when we reopen the file, or if we head it, let's head the first two lines from temp 1,000,000.txt. Indeed, it contains 0. Let's try it as the user Linux CBT, temp 1,000,000.txt, and it loads. And let's put 00, save the changes, and now the user is able to change the file. And let's head it as well. In fact, since we have it in our command history in this shell, let's just head it here. And there we see 000. So now the content can be manipulated by any user, which is not necessarily a good thing, but it demonstrates how you use change mod. If you know the octal notation, you can change the mode. Now let's change the mode using the non-octal notation, change mod. So this is 666 associated with the file. It's easiest to use this notation, but you can use other notation such as the removal of permissions, specific permissions like write, read, execute using minus, or the addition using plus. So for example, if we change mode, and let's go with U minus S, for example, or U minus W, that is, temp 1,000,000.txt. Let's see how this influences our permissions. Return to the shell, and you need to do this as the owner of the content. So if it's Linux CBT, use that user. Otherwise, it won't work. Now notice that the user who owns the content may no longer write to the file because we indicated the removal of that permission bit. And similarly, let's copy this and make another command. Let's just note removes owner's ability to write to the content. And similarly, this will remove other or everyone's ability to write to the content. But this will be, of course, O instead of U. Let's try this out. And we'll follow that up with an LSL temp 1,000,000.text. So now look in the last 3 bits, it's set to 6 or 4, that is. So now we've got 4, 6, 4 as our permissions. This means that everyone else, which includes Linux CBT 4, and otherwise, will not be able to write to the content. But any member of the group root will be able to write to the content. So let's drop that permission as well using non-octal. Octal is just simply simpler, but ChangeMod supports both. So ChangeMod G-W, the same thing, will apply to the group section. So removes group's ability to write to the content. And that's just simply G-W. So we'll just modify it here. And now the content's set to 444. So it's readable by everyone, but not writable. So how does that impact root? Well, let's nano the file, or at least try to modify it with nano. And let's add 000 and try to save the changes. Now notice we were able to save the changes. Let's head the first 5 lines from temp 1,000,000.text. And the changes were saved. And that's because regardless of what the permissions read, root can always make changes. Let's try to make changes as a user who recently was able to. We'll add 4 zeros. And of course, we're not able to write. And let's try to modify as this user, Linux CBT 4, adding, let's say, the same 4 zeros. And of course, we're not able to write. So you can make changes using ChangeMod using the octal notation or the English equivalent. To add or remove, just substitute plus to add, use minus to remove permissions, whether it's read, write, or execute. Now there are specific permissions that are set on directories. For example, let's take a look at our home directory. This user doesn't have anything created, so we'll do so as Linux CBT. We could save the file as a different file in a directory that we're able to write to. So notice, for example, this recently created directory 10,000,000.text or temp3 or temp2. They all have leading D values indicating that they're directories. But notice that they're also all executable, leading you to believe that perhaps the content is executable or is a script. Directories must be marked executable in order for users to enter them. It's the permission bit that's used to allow access to enter the directory. And then the other bits work the same way they work on files. So the fact that read-write is associated with the owner means the owner may read and write. So to enter the directory, the user needs to be able to execute and optionally to be able to read the content in the directory. And then beneath there you'll see that the other directories have inherited the same permissions. These permissions evaluate to 7, 7, 5. So that's a default mask that's associated with directories that are created by the user. Let's just copy this example as an example and just denote that it's 775. And oftentimes with applications, you'll find that administrators flag the content 777 so everyone can write, which is not necessarily a good thing, but sometimes it's the quickest way to get the application to work. So default directory permissions is octal 775 because it's read, write, execute, read, write, execute, read, blank, execute when you tally them up. So change mod will do that for you. Now let's just show you also chown, very important tool, which changes the ownership on content. So the file that we wrote in temp, if you recall, 1million.txt, is owned by root and the group root. Let's just LSL it again. And indeed, as a consequence of copying it, Red Hat Enterprise wrote the file to the directory with permissions associated with the user with whom we're logged in as. So to change the ownership, let's say, of the owner of the object, we use chown, or the group of the object, we use chown. So let's change the ownership of this object to Linux CBT, and of course that will allow the user to be able to write to the content. To change ownership, simply specify the name of the new owner, Linux CBT, on the content, and you can optionally specify the name of the group using a delimiter. So chown Linux CBT temp 1million.txt, followed by an LSL temp 1million.txt. This will show momentarily that Linux CBT has become the new owner of the content, which now means the user can manipulate the content. But notice that the permission is still set to read because we dropped the permission. So how does it influence the non-privileged user's ability to write to the content? Well, let's show you. Let's try to add a line. We'll save the changes. Doesn't work. So only root has that special privilege to bypass or circumvent the published permissions. So to influence this, as the non-privileged user, since we own the content, temp 1million.txt, we can change the permissions using change mod. Now since we want to grant ourselves the ability to write to the content, we need to add w, or 2, to read, which is 4, to make it 6. We can leave the group to 4 and everyone else to 4 or to 0 if we don't want others to access the content. So let's change it, and that has executed successfully. Let's re-LSL, and indeed Linux CBT now can make changes to the content. So let's exclamation nano to get the most recent instance and try to add that new record and save the changes to temp, and indeed it writes. And if we head the first, let's say, 7 lines from temp 1million.txt, indeed the content has been written. Now this content is still viewable by Linux CBT 4. That may or may not be a good thing. That is why there is the ability to remove the ability to read the content from any user. So we know that when Linux CBT 4 accesses the content, they do so under the auspices of everyone else. How do we know this? Well, let's take a brief look again. We'll LSL temp 1million.txt. We're currently logged in as Linux CBT 4, and that user isn't Linux CBT, so when the user attempts to access this file, they cannot use the first 3 permissions bits, or bits 2, 3, and 4, because the users don't match. And that's the UIDs don't match. Linux CBT 4 has a UID of 503, whereas Linux CBT has a UID of 500. Neither will the group permissions bit work, 5, 6, and 7, or 4, 5, and 6, because the GID doesn't match. 503 doesn't match 0. So that means it's the last 3 bits that are being used when anyone else tries to access the content. And it's currently set to read, which is why Linux CBT 4, or any other user for that matter, who doesn't match the owner nor the group, is able to access the content. So as the owner of the content, we can remove that permission octally or using the English translation. So for example, change mod, we could do, this is everyone else minus read, that's one way, temp 1million.txt. And let's follow that up with a stat instead of ls as an alternate means of enumerating permissions associated with the content. This is one way to do it. Another is octally, which would be just 640. So let's try this out as the owner of the content. And now when we take a look at the content, we see that it is flagged 640. It's even translated for us. It's read-writable by the UID 500. It's readable by the GID 0, any member of 0 GID. And no one else may interact with the content. The last 3 bits are turned off. So this now means that if Linux CBT4 tries to access the content using a recently invoked nano, it'll fail. It gives us a new buffer. It tells us it's not able to read temp 1million.txt. How about if we try to stat it to get some information on it? That we can do, but we can't see the content. Stat returns metadata, and that isn't harmful. At least doesn't seem to be harmful because it doesn't reveal the content. It just tells you data about, or gives you data about the data, or it is metadata. So it's read-writable by the owner, readable by the group root, and no one else may interact with the content. So there's nothing to stop us from statting it, nor from using LSL to enumerate its presence in the directory temp. But we cannot read the contents. If we try to cat it, for example, we're denied, as we should be. So now the content is more secure. And we could also drop root. We're the owner of the content. We could drop the permissions if we'd like. So we could do G-R or change mod. We want to be able to read-write as the owner and no one else to have access, 600, which is typically more secure than other forms of permissions. So 1million.txt, and then when we're done, let's stat it. Temp 1million.txt, and this will change the permissions to be 600, which is much more restrictive. Now, this changing of the mode may only be performed by the owner of the content. To prove it, let's try it in this shell as the user Linux CBT4. It doesn't work. And we should also add, and also by root. Root can always perform these tasks. Now let's do it as the owner. And now the new stat shows that the permissions associated are 600. So it's now set. This leading bit that we haven't discussed in the permission set allows us to define other classifications of permissions like set UID, set GID, or sticky bits, for example. With 0, it means it's just a regular file, which could be directory, character, block, etc. So now it's 600, and that means no one else can interact with the file. But again, root can always interact with the file. Temp 1million.txt. Nothing prevents root, and root can always change the permissions of the file. So let's chown, or change mod, 644 temp 1million.txt, and then echo the exit status, and you'll see that there's nothing to prevent that from happening, which means that root is always a vector into content. Now let's take a look by statting temp 1million.txt, and you'll see that it's been flagged 644. And if you compare the timestamp to the access and change times, you'll see that it was recently touched. So this has been an intro into change mod, chown, the bits of permissions that are associated on Linux systems. We're going to continue our study of these items and look at symlinks and hard links as means of linking to content across your system.